Students, welcome to another video. Today we will discuss the definition of interior set. Before that, we will take one or more examples on the open sets. So first example is a non-empty set is a non-empty subset of real numbers R is open. Is the non-empty subset of R is open. So non-empty is a non-empty subset of R instead of non-empty subset, non-empty finite subset. Question is a non-empty finite subset of R open? Is a non-empty finite subset of R is open? So we know that by previous theorem we have seen that space without finite point is open, that is the metric space excluding finite number of elements in that space, the remaining set is open set. But in R finite set we have to check this finite subset of R is open or not. So for that we will take one finite subset of R. Let A be a finite subset of R. So A is of the form, suppose x1 x2 up to xn. This is the finite subset of R, and we can clearly see that any finite subset of R is not open, because we know that the open sphere in R, that is if we draw the open sphere in real line considering any element as center, then that open sphere is open interval, and we know that open interval of real number contains infinitely many points, but this A has only finite number of points, so that open sphere not totally lies inside this. So our set finite subset of metric space R is not an open set. So we can contrary suppose, we will contrarily suppose that this A is open, set. So therefore now A is open set, so by definition of open set we can show for any element of this A, that is x1 x2 up to xn, and there exists some radius greater than 0, so that open sphere lies inside A. Therefore for all these xi's belongs to A, there exists some radius greater than 0, such that open sphere centered at xi with radius r lies totally inside the A for every I running from 1 2 3 up to n. That is, the open sphere in R is the open interval center minus radius and center plus radius, that is xi minus r comma xi plus r. This interval lies inside A. But is this possible? No, it is not possible, because this open interval contains infinitely many points, whereas this A set contains only finite number of points. So this is not possible, which is not possible, because since the interval xi minus r and xi plus r, xi plus r contains finite, here this interval contains infinite number of points, infinite number of points, whereas this A contains only finite number of points, hence this open sphere centered at xi with radius I does not lie inside A. So this A is not an open set, not an open set in R. So from this example we can say that any non-empty finite subset of R is not open. So similarly we can prove the next example. Similarly the next example is the set of rational numbers. It's the set of rational numbers open in R. Is the set of rational numbers open in R. What about irrationals? What about irrationals? Here, similarly, like previous example, if we consider the set of rational numbers and take one of those rational numbers and considering that number as center and taking any radius r and draw the open sphere, that open sphere will be our open interval and that open interval contains some rational, some irrationals. So if we take any rational number and considering that number as center and take some radius r and draw the open sphere, that open sphere will be our open interval and that open interval clearly contains some rational numbers, some irrational numbers, because in between any two rationals there are some irrational numbers. So that set, that open sphere does not totally lies inside the set of rational numbers because there are some irrationals. So our set of rational number is not also not open in R. Similarly irrationals, the set of irrational is also not open in R. So this is for your homework. You have to prove, that is you have to take the set of rational numbers q and for and contrary you have to suppose that that set of rational numbers is open, and similarly for rational numbers for all x belongs to that q there must be some radius greater than 0 such that that open sphere lies inside q. That open sphere is again now your x minus r, x plus r, that lies inside q, which is not possible because this interval contains some rational numbers also. So this interval not totally lies inside q. So similarly you can say that, so there is only one reason here, since this interval, for this example you can write, since this interval contains some rational points whereas that q contains only rational points, so that SR of x does not lie inside q. Similarly you can show that similarly irrationals are also not open in R. This is for your homework. Now the next definition is interior offset. The next definition is the interior offset, interior of a set, interior of a set. Now for suppose this is metric space xd. For this space, suppose this is the some set, subset of metric space, suppose this is S is subset of this metric space xd, then we say that any element of x, element of x is interior of S. Any element of metric space xd is interior whenever that point, that x lies inside this C. Suppose this is the interior, this is again interior of C. You can clearly see by our naked eyes, that is the these points are interior, that is in the boundary of yes, under the boundary of yes. So these are the interior points, but this boundary point is not interior point. The proper definition of interior point is this x said to be interior point of yes if there exists some radius greater than 0 such that that radius, that open sphere centered at that point x and with radius r, that open sphere lies inside yes, then we say that yes is, then we say that that element x is interior of S. See, the definition of interior of set and the definition of open set is nearly equal. The definition, the proper the theoretical definition of interior of set is yes is let yes, this yes be the set of, yes be the set of metric space xd, yes be the subset of metric space xd. We say that, we say that x belongs to S, suppose this x belongs to S is an interior point of set yes, interior point of set yes, if if there exists some radius greater than 0. I'm always saying some radius because for this x radius should be some less number, for this x radius is less. There is no fixed radius, for every different point there may be another radius, so there exists some radius greater than 0 such that the open sphere centered at that x with radius r lies inside this point x, this S. So also the notation of that interior of set yes, suppose 1 2 3 4 up to this infinite number of points are interior of set yes, then yes interior is denoted by the set of interior points, the set of interior points of yes is denoted by, is denoted by yes interior, that is yes interior. This is notation yes, here small 0 small o, yes interior, this is notation of interior of set yes. The point x belongs to S is said to be interior if there exists some radius r greater than 0 so that that open sphere lies inside this yes. So if you can compare the definition of interior of set and the open set, then you can clearly say that interior of set yes, that is yes interior is open set, because for all x belongs to the set yes, for all x belongs to that set yes, there exists some radius greater than 0 such that SR of x lies inside C. If for every s belongs to, every x belongs to S, the open sphere centered at x lies inside C, then we say that this x is the interior point of S. And if we collect the all interior points of set yes, then we can say that this S interior is open set. So if this is the definition interior of set. Set these points in, these points which are interior to this S are said to be set of interior points. So that x is said to be interior whenever there exists some radius greater than 0 so that SR of x lies inside C. So you can write one note here, yes interior is an open set, because clearly we can say that yes interior satisfies the definition of open set, that is for every x belongs to that yes, there exists some radius greater than 0 such that open sphere lies inside yes. So yes interior is open set. Now next we will take one example. For that, suppose this is the first note, we will write the second note. Second note, for any set A, for any subset A of metric space XD, for any set A interior, suppose this was our set yes whole yes, and yes interior means just excluding the boundary point, the remaining interior point are the set of interior points of yes. So yes interior, so yes interior is the set, this set which is just excluding the boundary, just subtracting the boundary from yes, we get the set of yes interior. And clearly we can say that this interior yes interior is subset of this whole set yes, because that yes interior lies inside yes. So yes interior is subset of yes. For any set A of metric space XD, A interior is always lies inside yes. This A interior is always contained in A, always. This A interior is always contained in A. This is the second one. Now the next example is one of the most important example. Let XD be a metric space. XD be a metric space. XD be a metric space. Then prove that. Then prove that the first condition is A is open. XD be a metric space, then prove that A is open. A is subset of metric space XD. A is open set if and only if and only if A is equals to A interior. A is said to be open set if and only if A is equals to A interior. And the second statement is for any set A, for any set A the set A interior is the largest open set, is the largest open set, largest open set contained in contained in A. A is said to be open if and only if A is equals to A interior. So suppose this S is said to be open. Yes, when we say that S is open, whenever S and S interior are the same elements. Open set does not contain its boundary point. Suppose I will, this is some another metric space XD. Then this set is said to be open. One thing, just clear, make sure that the open set does not contain its boundary point. So this is the set yes, then this yes is said to be open. Yes is open means yes does not contain its boundary point, and we know that the interior of yes also does not contain its boundary point. So this is the interior, just excluding these boundary points, the remaining interior set is yes interior. Also this yes does not contain this boundary point, so clearly we can say that A is equals to A interior. Now the second statement is for any set A, the set A interior is the largest open set contained in A. We know that this A interior, suppose this is A, right? Instead of yes, we will take A. Suppose A interior is the set of all interior points. So just excluding this boundary, A interior is the whole set. So clearly we can say that A interior is the largest set, because just excluding the boundary points, all the interior points are in A interior. So clearly A interior is the largest set, and by definition of interior of set, we know that or by first note, A interior is yes interior is open. So here A interior is largest set, also that A interior is open. So A interior is the largest open set that contained in A, that is that lies in A. Now to prove these results, this is the A interior, this set is A. Interior means all the interior points, interior just excluding the boundary points, just subtracting the boundary points from this set A, remaining set is our A interior. Now the solution. So to prove the first if and only if condition, first of all we will suppose A is open, then we will prove A is equals to A interior. In converse part we will suppose this and prove this. Now suppose A is open set. A is an open set. Now by definition of open set, for all x belongs to that A, there exists some radius greater than 0 such that the open sphere centered at x lies inside A. This is the definition of open set. SR of x lies inside A. So this says that every point of A, for all x belongs to A means every element of A, for every element of A there exists some radius greater than 0 such that SR of x lies inside A. So again the definition of interior of set is that set x belongs to that yes is said to be interior point whenever there exists some radius, so that open sphere centered at x lies inside that yes. Here for every element of A there exists some radius greater than 0 such that this open sphere lies inside A. So clearly we can say that this x is interior point of A. But this is for all, because A is open set, so for all x belongs to, so this implies that each element of A is interior point of A, that is each element, that is, or you can say that every point of A is interior point of A, interior point of A, that is our x belongs to A interior for all x belongs to A. For every element of A is interior point of A. So this implies that A is equals to A interior, because if you try to prove that, so our claim is A is equals to A interior. If you prove A is contained in A interior and A interior is contained in E, A. So this by second note A interior is subset of A, but here we have shown that X belongs to A and that X belongs to A interior. So A interior is also A is also contained in A interior. So from that two cases you can clearly say that this. There is no need to do that. Just write this. Since we know that A interior is always contained in A, we have to prove A is contained in A interior. Taking that element of A, S or of X lies inside A, that X belongs to A implies X belongs to A interior. So A is subset of A interior, and that is hence the proof. So instead of writing that, take this open set. By using definition of open set, we can write this S or of X lies inside A. So this by definition of interior point, we can say that every element of A is interior point of A, hence A is equals to A interior. Now conversely, suppose that A is equals to A interior. A is equals to A interior. To show that A is open set. So our claim is A is open set. A is open set. So to prove any element as open set, we just take that element. So to prove any set as open set, we take one element of that set and draw the open sphere centered at that X, and if that open sphere lies inside this set, then we can say that the set is open. So let X belongs to A, be any arbitrary element of this set A, be any arbitrary element of A, but this A is equals to A interior, but we have supposed that A is equals to A interior. So X belongs to A and A is equals to A interior implies that X belongs to A interior. Since X is element of A and A is equals to A interior, so X belongs to this A interior. Notation must be proper. X belongs to A interior. Now by definition of interior of set, by definition of interior of set, we can we can use the definition, and so therefore there exists some radius greater than 0 such that this open sphere centered at X lies inside A, by definition of interior of set, there exists some r greater than 0 such that S r of X lies inside. This is the definition of interior of set. We say that this X belongs to S, B is an interior point of S if there exists some radius greater than 0 such that S r of X lies inside S. If this open sphere lies inside S, then we say that X belongs to S interior. So using this S r of X lies inside A, that is, so this X belongs to A and there exists some radius greater than 0 such that S r of X lies inside A implies that A is an open set. A is an open set. This is the proof of first statement. This is important example. If your exam holds offline, then these two statements are maybe asked for 5 marks. So this is the proof of first statement. Now we will prove the second statement. Second statement is A interior is the largest open set contained in A. Now to prove the second statement, we know that we have to prove that A interior is the largest open set contained in A, but we know that A interior is open set because by previous note we know that for any set A interior is an open set in A, is an open set in A. A interior is an open set in. Now we have to prove that this A interior is just the largest. A interior is open, and if that A interior is also largest, then we can say that A interior is largest open set. To show that A interior is the largest open set contained in A. we have to prove that A interior is largest. Here A interior is open set. We now just only we have to prove that A interior is largest set in A. If to prove that A interior is largest, suppose there is some another open set in A, and if that arbitrary open set is lies inside A interior, then we can say that A interior is largest. To prove this A interior is largest, we will take one open set in A, that is suppose this U, and that arbitrary open set U again lies inside A, then we can say that A interior is largest, because this A interior contains all the other open sets. So let that U be any another, let U be a open set of, so open set in A. U be any another open set in A. To show that this A interior is largest, we have to show that this U is contained in A interior. To show this A interior is largest open set, we have to show that this U is lies inside A interior. And to prove this U is subset of A interior, we will take one element of U and we will prove that element is also belongs to A interior. Now let that X belongs to U, and we have taken U be an open set in A. So here X belongs to U and U is open set. Therefore, by using definition of open set, we can say that there exists some radius greater than 0 such that SR of X lies inside U. Let this X belongs to U, and since our U is open, therefore there exists some radius greater than 0 such that the open sphere centered at X with radius R lies inside U. SR of X lies inside U. But this is U be an open set in A, that is this U was our subset of A. U be an open set in A means U is the subset of V as open subset of A. So U is inside A, but U lies inside A. This SR of X lies in U and U lies in A, implies that SR of X lies inside A. SR of X lies inside A. Here U is an open set in A, so U is subset of A, and we have to show that A interior is largest open set. So to prove this U is lies inside A interior, we have taken X belongs to U. So by using definition of open set, we can write there exists some radius greater than 0, so that SR of X lies inside U. But sorry, but this U lies in A, so this SR of X is subset of U is subset of A, implies SR of X is subset of A. So this SR of X is subset of A implies that this X is interior point of A. So this implies X is an interior point of A. That is, for any X belongs to A, if there exists some radius greater than 0, then that open sphere lies inside A, then we say that this X is interior point of A by definition of interior point. So this implies our X belongs to A interior. X belongs to U and this X belongs to A interior means U is subset of A interior. So for any open set of A, that open set lies inside A interior, implies that A interior is the largest open set. This implies A interior is the largest open set, because A interior is open set, largest open set in A, largest open set containing A. Hence the solution of this example. This is the important one. Now the next example is, this example can be asked for 2 marks. Find the interior of the following sets. Find the interior points of the following sets. of the following sets. First set is close interval 0 and 1. Close interval 0 1 following sets, following subsets of R, suppose this R, following sets of R. This is the close interval 0 1 which is subset of R. So to find the interior points, let A is equals to this given set close interval 0. Then this is the close interval, suppose on real line close interval 0 1. We know that the interior points of the set A are just excluding these boundary points, all the remaining interior points are the set of interior points. So A interior, that is the interior point of 0 1, is just excluding the boundary point. The boundary points are 0 and 1. So excluding that 0 and 1, all remaining points are the interior points of this close interval. So A interior, that is the interior points of close interval 0 are open interval 0 1. Since this 0 does not belongs to A interior, also this one does not belongs to A interior, because if your 0 belongs to A interior, then we have to find some radius greater than 0, so that open sphere centered at 0 must lies inside this set of interior. But for 0, if we take any smallest radius, then the open sphere goes outside that set. So 0 does not belongs to A interior, similarly 1 does not belong to A interior. If you take the second example as open interval 0 1, then the open interval 0 1's interior points are open interval 0 1 itself, because this open interval is open set in real line and A is open if and only if A is equals to interior. So this is open set. Now the next example is, what is the interior? Is the interior points, what are the interior points of Q in R? Set of rational numbers in R. What is the interior points of Q in R? Now if we take any element of Q, and for suppose this x belongs to Q, is any element of Q, be any rational number. Suppose this is any rational number. To prove this element as interior point, we have to find some radius greater than 0, and that open sphere SR of x must lies inside the Q, be any rational number. Therefore for any smallest radius possible, for any r greater than 0, the open sphere in R is open interval. So SR of x is that x minus r, x plus r, and again this open interval contains some irrational points. So this open sphere does not totally lies inside Q, hence this x does not belongs to Q. So any arbitrary element of Q is not an interior point of Q. X does not belongs to Q interior Q. So this implies that interior of Q in R is a empty set. Interior of Q in R is empty set. Similarly, the for irrational numbers, interior of irrationals, interior of irrationals in R is equals to phi, is null set, empty set. So that's it for today.